differs, okay, electrostatic potential differs with respect to the different kinds of charge configuration. So you could have it before because of the single point, a single point charge or a system of charges, or we also saw how it varies with if you have a charged spherical shell, a thin charged spherical shell. So we saw all this. So now we will move on to something called the equipotential surfaces. So in simple terms, equipotential surface is a surface which has a constant value of potential at all points on the surface. Okay, so if you consider this, I'll just put on the laser pointer. Okay, so if you're considering these surfaces over here, okay, so if you measure the potential across any point or potential at any point that is there on this surface, the value of the potential is going to be the same. Okay, so since all the potential values on this surface is equal, that is why this surface is called an equipotential surface. Okay, so similarly you can see these concentric circles. So all these concentric circles, maybe the potential value of this surface is different than this surface, okay, and this is also different, but any point on these surfaces will have equal value of potential. Okay, so suppose if you are considering a single charge Q, you can see that we had seen this even in the previous content, that the potential is given by 1 upon 4 pi epsilon 0 Q by R. Okay, so the potential due to the single charge Q varies as an inverse of the distance between, say, the point and the charge, where the point where we are calculating the potential for. Okay, so this R is going to differ for all the surfaces, and in that way you can get the potential value for each of these potential equipotential surfaces. Okay, so if R is constant, okay, so at this point the R is constant, at this point the R is constant, at this point the R is constant. Okay, so the V will be constant. That is why we can say that the potential, because it depends on the distance between the point that we are calculating the potential at and the charge, owing to which it is being, present over there. So that is constant. So we can say that the equipotential surfaces of a single point charge are concentric spherical surfaces centered at the charge. Okay. So electric field, as we know, is actually going to be these normal to the equipotential surfaces. Okay, through that point the electric field, okay, as we know, like from, suppose we are considering this as a positive charge, okay, so we know that the electric field is going to be radially outwards, and since it's radially outwards, you can say that actually the electric field is it is perpendicular or normal to the equipotential surface. Okay, and this is true for any charge configuration. Equipotential surface through a point is normal to the electric field. Okay, so this is something that is, it's simply understood owing to the definition of both electric field and as well as equipotential surface. Why, if we consider that the field is not normal, okay, then there will be one non-zero component along the surface. Okay, and then to move the charge, like suppose any test charge against the direction of this field component, there needs to be work done. Okay, but that is actually against what the equipotential surface actually defines. With equipotential surface, we say that there is no potential difference between any 2 points on the surface, and because there is no potential difference, there should be no work done in required to move a test charge on the surface. Okay, as we had seen that work done in bringing or moving one point to another point, okay, that is actually the it is equivalent to the electric potential or electric potential difference between the 2 points. Okay, so if the field is not normal, so there will be a difference between the potential of, say, one point here. Okay, so suppose we are considering one point here, okay, and the other point here. If the if the if the electric field, okay, is not normal, okay, so there will be another component along this surface, okay, as we just said, okay, and because the because of that, work needs to be done to move the one charge from this point to another point, okay, but since the equipotential surface has equal potential value at all the points, okay, that means the work done should be zero, and because of that the potential difference should also be zero. So that is why it reiterates the fact that electric field is normal to the equipotential surface. Okay, over here you can see an example that equipotential surfaces for a uniform electric field. Okay, so these are your equipotential surfaces, these planar surfaces, okay, and this is the electric field direction. You can see that the electric field is perpendicular or normal to these equipotential surfaces. These are some other examples of configurations. Okay, so this is a dipole. As you know, dipole is a pair of oppositely charged and equal charges. Okay, so each of these charges have the equipotential surfaces. Okay, they are again concentric circles, and suppose you have two identical positive charges or negative charges over here. Okay, so their equipotential surfaces are going to appear like this. They are not going to intersect in a way, okay, but they could be very, very close to each other. So now we saw that electric field is normal to the potential. Okay, so there should be a relation between the electric field and the potential, okay, when we are considering a system of charges. So if you consider two closely spaced equipotential surfaces A and B, okay, so suppose this is one surface and this is one surface, okay, so this is your B and this is your A. Okay, and the potential values will be, suppose this is V and this is V plus uh, del V. Okay, del V is the potential difference between the potential surfaces, the values of potential between A and B surface, the equipotential surfaces. Okay, so del V is the change in V in the direction of the electric field. Okay, so suppose we are considering the electric field in this direction. Okay, so this is and del L is the perpendicular distance of the surface A from P. Okay, so suppose you take a point P over here, okay, or here, okay, let's consider that the below one. Okay, so this is going to be your del L. Okay, so it is a perpendicular distance from the surface A, perpendicular distance of the surface A of P. Okay, so now suppose we are moving one unit positive charge along the perpendicular line that is being drawn from say suppose from surface B to surface A. Okay, so electric field is going from surface A to B. Okay, it's in this direction, but we are moving the charge from B to A against the electric field. Okay, so there is going to be work done in this process. Okay, so the work done is going to be the product of the electric field and the del L, that is the distance that it is traveling. Okay, so now this work is going to be equal to the potential difference between the equipotential surfaces. Okay, so VA minus VB. So now when we write it in the equation form, so E del L is equals to V minus V plus del V. Okay, so because we know this is the potential values of, this is for VA, this is for VB. Okay, so what we are left with is a negative del V. Okay, and hence we can see that it is going to be del V by del L. Okay, now we are considering this as positive. Okay, so we are only considering the magnitude of it over here. Now what we can conclude from this derivation and this kind of system is that electric field is in the direction in which the potential decreases steepest. Okay, steepest as in the potential decreases drastically, okay, very quickly, and the magnitude is given by the change in the magnitude of the potential per unit displacement normal to the equipotential surface. Okay, so as we saw, the we are only considering the magnitude of the change in the potential, okay, per unit displacement, which is normal to the equipotential surfaces, okay, at the point. Okay, so this is how we can understand the relation between electric field and electric potential. Okay, so now we consider potential energy of a system of charges. Okay, so now we are going to consider, or we are going to understand what is the potential energy, okay, in different kind of charge configurations. So we, for simplicity purposes to understand, we are going to consider only two charges, okay, positive charges Q1 and Q2. Okay, and they have some position vector, okay, R1 and R2 relative to some origin, that arbitrary origin that we can take. Okay, so we are first going to understand the work done by the external forces, okay, in getting this configuration first. Okay, so suppose your Q1 and Q2 were at infinity. Okay, so now we are actually first going to bring Q1 to this point. Okay, so there is going to be some um, work done to get Q1 over here. So suppose Q2 is not yet over here. Okay, so there is no electric field as such. There is no external field, external field that we have to do the work against. Okay, so that is why there is no work actually being done in bringing Q1 from infinity to this point, to this position. Okay, so that is going to be 0. So if you remember, work from getting 1 point from infinity to, suppose, say, point P is actually going to be just equal to the potential that is there at the point where the charge is being brought. Okay, so that is why the work done, okay, or in the terms that we are concerned with, the potential produced when you bring the charge Q1 to this point from infinity is going to be given by the normal equation that we have seen, that V is equals to 1 by 4 pi epsilon 0 Q1 upon R1P. R1P is the distance, okay, that from any point in space, okay, is the distance of a point P in space from the location of Q1. Okay, suppose we brought it from any point to the current point, so that is R1P. Okay, so now Q1 has already come at this point. Okay, so now when we do work, okay, in bringing this charge Q2 from infinity to the point R2, okay, that is going to be Q2 times the potential at R2 due to Q1. Okay, so this again goes back to supposing that this is now a source charge and we are bringing a test charge Q2 from somewhere till here. Okay, and this is going to be present when we are doing the work in bringing Q2 from one place to any place in the space, any point in the space to this point now. Okay, so the work that is being done is going to be actually the product of the charge that is being brought. Okay, the charge that is being brought multiplied by the potential that is there at this position due to the presence of Q1 that is already brought here. Okay, so work done on Q2 is going to be 1 upon 4 pi epsilon 0 Q1 Q2 by R12. Okay, R12 is actually now the distance between Q1 and this point where we are bringing the charge Q2. Okay, so R12 is the distance between points 1 and 2. Now we know that electrostatic force is conservative in nature. Okay, so the work done is not going to make difference, but it is going to get stored in the form of potential energy of the system. Okay, so now what will be the potential energy of this system where we have brought two charges from different points to this point is going to be given as the 1 by 4 pi epsilon 0 q1 q2 by r12. Okay, so now suppose if you bring q2 first, okay, suppose you had brought q2 first, so the work done or the potential in the space due to that work, okay, of bringing q2 first would have been v2 is equals to 1 by 4 pi epsilon 0 q2 by r2p. Okay, suppose that would have been the equation if we had brought q2, and then if you brought q1 after that, okay, so that would have also been affected because of the presence of q2 already there. Okay, so now when you're bringing q1, okay, so the work done would be equal to the potential at this point, okay, at this point due to the presence of q2 already there. Okay, so then this equation would have changed to work done on q1 is equals to 1 by 4 pi epsilon 0. Again, it would have been say q1 q2 by r12. Okay, so it would have been the same whether you bring q2 first or q1 first. Okay, so it is not going to change the potential energy. Okay, so it would be same. More generally, the potential energy expression is unaltered whatever path you choose or in whatever kind of configuration you try to bring it about, because we had also specified before that the electrostatic force, okay, and the work done to get the potential difference that we try to find, okay, that is independent of the path that is being followed by in getting the charges to the points of concern. Okay, so this is the potential energy of a system of charges. Okay, U is potential energy, V is just the potential. Okay, so as I said, now if we are considering the signs of the charges, if you have q1 q2, if it is more than 0, okay, so the potential energy will be positive obviously, and if you have like charges also, okay, so q1 q2 the product could be more than 0, okay, if both of them are positive, but the electrostatic force is repulsive. Okay, and that is why you need a positive amount of work to work against the electrostatic force that is there to bring the charges from infinity to the finite distance apart. Okay, so if your q1 q2 actually whether it's positive or negative, okay, plus plus is going to be more than 0, minus minus is also going to be, when you take in the product form, it is going to be more than 0. Okay, so if the electrostatic force that is present between the two charges, okay, is repulsive in nature, so the work done in bringing about the charges from infinity to this charge configuration is always going to be positive. If you have unlike charges. Okay, so it could be, it is actually the product would be less than 0. Okay, so the electrostatic force is attractive and positive amount of work is needed against this force to take the charges from the given point to infinity. Okay, so the amount of work, actually a negative amount of work is needed for the reverse path. Okay, so they are already, being attracted. Okay, so if we actually want to take these charges away from each other, okay, because they are attracting each other. Okay, suppose we consider a situation where this is minus and this is plus. Okay, so these are attracting. Okay, so any work that you do in getting these charges to move away from each other, okay, you want to take this charge away from this, away from this to infinity. Okay, so again the external force that you are going to use to the, to get the work done is going to be, in the reverse or in the opposite direction, and that is why the work that is being done to remove this charge from this point and to bring it to the infinity is going to be positive. But when we are trying to get the charge, okay, from say infinity to this point is actually going to be negative. Okay, so a negative amount of work is needed for the reverse part, that is from the infinity to the present location. So the potential energy then becomes negative, and that you can see that if the product of Q1, Q2 is negative, your potential energy is going to be negative. Okay, so if you have, suppose, a system where you have multiple charges. Okay, so suppose we are considering three charges right now. Okay, so Q1, Q2, Q3, and these are located at R1, R2, R3 respectively. Okay, so first again we bring Q1 from infinity to R1, no work is done. Okay, so your V1 is going to be 1 by 4 pi epsilon 0 Q1 by R1P. Okay, we saw this before. Now, if we are bringing Q2 from infinity to R2, now the work that is going to be done is actually going to be the product of the charge that is being brought, okay, Q2 over here multiplied by the potential that is already there at the point because of the charge Q1 which has been brought before. Okay, so it is going to be Q1 plus Q2 upon R12. Okay, so if you kind of only consider the distances that is given. Okay, suppose we are considering at one point, okay, at any point P. Okay, so that would be Q1 by R1P plus Q2 upon R2P. Okay, so suppose we are considering the potential at any point P due to the produced by the charges Q1 and Q2. So it is going to be an addition. Okay, superposition principle, if you remember. Okay, so that using that we are going to get this equation. Then again the work done in bringing the charge, okay, Q3 from infinity to point R3, okay, is going to be Q3 times the potential due to both charges 1 and 2 at R3. Okay, so Q3 multiplied by the potential due to both charge 1 and 2 is going to be given in this form. Okay, so the total work done or is going to be stored in the form of potential energy in the charge now. Okay, so again using the superposition principle, and we are going to get an algebraic sum of all the potentials that we have calculated. So this is your V1, this is your V2. Okay, so this is your V2 at R2. Then this is your this entire thing is your this is due to the charges Q1 and Q2. Okay, potential at R3 when you are bringing Q3. Okay, and potential due to the presence of Q1 and Q2 when you are bringing Q3 from infinity to point R3. Okay, so we add all these up and this is going to give you the potential energy. of the system of charges. Okay, so because of conservative nature, the final expression for U is independent of the configuration is assembled. Okay, so if you try other configurations, suppose you bring Q2 first or you bring Q3 first. Okay, so actually this is not going to change, it is going to be the same. Okay, so this is going to be the same. So the potential energy is actually the characteristic of the present state of the configuration and not the way the state is achieved. Okay, so this is again a reiteration of the conservative nature of the electrostatic force. So now if we want to know, okay, the potential energy in an external field. Okay, so till now what we have been speaking about, that we know what is causing the electric field, that is we are considering while calculating the potential. Okay, suppose the suppose the electric field that is present, okay, is not actually produced by the charges that we are considering. Okay, suppose we don't know. Okay, so suppose the E is being produced by sources external to the given charges. Okay, so the external electric field and the corresponding external potential V will vary from point to point. Okay, we don't know, these are unspecified. Okay, so then by definition we can say that V at a point P is the work done in bringing a unit positive charge from infinity to the point P. Okay, so this is what we know. So if you are trying to do the work in getting a charge, say Q, from infinity to point P, okay, in an external field. Okay, so this is your P, okay, and you're bringing the charge from, say, infinity. Okay, this is your Q, you're bringing it to point P. Okay, from infinity in the external field is Q into V. Okay, so V is the potential at point P. Okay, and this is going to be the work done in bringing a unit positive charge from infinity to P. Okay, and the work done is going to be Q into this potential. Okay, but what is the potential energy of Q at R in an external field is going to be with respect to the distance QV R. Okay, where VR is the external potential at point R. Okay, suppose you are considering one origin, say somewhere here. Okay, so this is your origin and this is your R. Okay, so potential energy of Q at R in an external field is going to be QVR. Okay, so if you consider an electron with charge Q, okay, which is being accelerated by the potential difference of 1 volt, it would gain energy, the potential energy, as 1.6 into 10 raised to minus 19 joules. Okay, because your del V is 1. Okay, so if you multiply Q into del V, okay, so that is going to give you the potential energy. Okay, and energy is going to be given in the units of joule. Okay, and this is the work done. Okay, and the energy. So the unit of energy is then defined as the electron volt, or 1 eV. Okay, so 1 eV is actually equals to 1.6 into 10 raised to minus 19 joules. Okay, so this is actually when we are kind of using units or as electron volt. Okay, so we consider this unit when we are trying to study atomic particles, like atomic particles, nuclear particles. Okay, so this is where the unit EV, electron this electron volt, is going to be useful. Okay, so this is because this is how you can see that the potential energy in an external field can be calculated for a single charge. If you now have two charges, okay, a system of two charges, okay, that was only one charge, now you have two charges, okay, so you have Q1 and you have Q2, okay, so, and we are trying to, uh, we are trying to find out what is going to be the potential energy due to an external field, okay. We don't know the source of the external field, okay, it's there. So, and these are located at R1, R2, okay, and the distance between them can be say as R12. Okay, so first we will again as usual calculate in bring the work that is being done in bringing the charge from infinity to Q1, okay, at position R1, and the work done in this step would be Q1 into V R1. Okay, next we are going to consider getting Q2 from infinity to R2 to this position. Okay, work is done. Now the work is done, being done against the electric field that is there due to Q1, okay, as well as the external electric field, okay, that is present. So first, if we try to understand the work done against the external electric field, we saw for point charge in the previous slide, okay, so it's going to be Q into V, okay, so Q2 into V at R2. Okay, now work done on Q2 against the electric field due to Q1 is going to be Q1 Q2 upon 4 pi epsilon 0 R12. This also we saw when we were trying to see what is the potential energy at a point due to two charges. Okay, or potential energy of a charge because of two charges, or because when you are trying to get Q2 to a position, okay, where an electric field is already there due to Q1. Okay, so, and as I said, R12 is the distance between Q1 and Q2. So then again, by using superposition principle for fields, okay, so we can add up the work done on Q2 against both the fields, the electric field, the external electric field, and the electric field due to the charge Q1, okay. So the total work that is done in bringing Q2 to R2 can be given as the sum of the both of the work that is being done. So Q2 VR2, that's Q1 Q2 upon 4 pi epsilon 0 R12. Okay, and thus the potential energy of the system is going to be the is equals to the total work done in assembling the configuration. So now the for the entire system of charges that we have, okay, so the potential energy due to the potential energy of this system in the effect of the of an external field is actually the sum of the work done on both the charges. So Q1 V1 R, okay, Q1 V1 R is the work done on Q1 in bringing it from infinity to the point R1. Q2 V2 R2 is the work done on Q2 in getting it from infinity to the point R2, okay, uh, against the external field, okay, this is also against the external field, the first term is also against the external field, and this is also external field, and this term is actually the work done on Q2 in getting it from infinity to point R2 against the field that is there due to the presence of charge Q1. Okay, so this is going to be your potential energy of the system when we are considering two charge systems, okay, in an external field. Now we are going to consider the potential energy of a dipole in an external field. Okay, so dipole, if you remember, so one is going to be positive and one is going to be negative. Okay, so suppose there are two charges, they are equal in magnitude, so both of them are Q. Okay, and the distance between them is going to be 2a. Okay, dipole moment is given as 2qa. Okay, and so this is how we find the dipole moment that is there. Okay, as you know that if we keep a dipole, electric dipole, in a uniform electric field, okay, so the dipole is going to experience no net force. Okay, so there is no force acting on these charges or due to the charges, because you know, they are negatively unlike charges. Okay, and so that is why it will experience a torque. Okay, so it will experience a torque. And what is torque? Torque is given as the vector product of the dipole moment vector and the electric field that is present. Okay, it will try to rotate the dipole. Okay, so the torque is going to try to rotate this dipole, okay, in the direction in alignment with the electric field. Okay, so so now we are considering, suppose there is an external torque, okay, that is there because of an external field. Okay, so it is applied in such a manner that it neutralizes the torque. Okay, an external torque is being applied which is neutralizing this torque. Okay, and it is rotating it in the plane of the paper, okay, from say an angle theta 0 to theta 1, okay, at an infinitesimally angular speed, okay, without angular acceleration. Okay, so there is not going to be an angular acceleration, okay, because the speed of the rotation is very low, but there is a change in the angle. Okay, so the amount of work done by the external torque, okay, will be given by work, okay, and integrating it from theta 0 to theta 1. Okay, so we are integrating the external torque, okay, with the theta, okay, with respect to the angle. Okay, so then again theta external is going to be your PE sine theta. Okay, see, it's a vector product. So if you put it in the, you know, when you want to just find the magnitude of it, you are going to put it as PE sine theta d theta. Okay, so when you integrate it from theta 0 to theta 1, you are going to get this expression. Okay, so this is the amount of work done by an external torque. Okay, and this work is then stored in the system as potential energy. Okay, so we are now going to consider the potential energy u theta, okay, with an inclination theta for a dipole. Okay, so as we saw, the potential energy, okay, you know, is suppose we take an angle where the potential energy is 0. Okay, so we can take that, and the natural you know, for it to be 0, okay, if you take theta 0 as pi by 2, okay, so the cos of pi by 2 is going to be 0. So then we can write it as just the function, or just it depending on the just the theta. Okay, theta is the angle with you know, which the torque is trying to rotate the dipole with. Okay, so then it can be given as a PE cos theta. Okay, and then we get it as minus dot E. Okay, so this is your vector form. Okay, so this is your dot product. So u theta can be given as the dot product of P of the dipole moment vector and the electric field. Okay, and the negative sign is there. Okay, so now applying the, you know, superposition principle, and where we are having, you know, two charges, okay, plus q and minus q. So the potential energy will now be actually you know, the charge multiplied by the potential difference between the two point charges, okay, between the say one is at r1 and one is at r2. Okay, so that is going to give you q square upon 4 pi epsilon 0 into 2a. Okay, so this is what we are getting, where r1 and r2 will denote the position vectors of the plus q and the minus q. Okay, so now we can see that the potential difference, okay, between positions r1 and r2 actually equals the work that is being done in bringing a unit positive charge against the field from R2 to R1. Okay, so this is what we are trying to get. What is the potential difference between the point R1 and R2? Okay, when we are trying to bring a unit positive charge against the field that is there, external field that is there. Okay, so the displacement is parallel to the force. Okay, so the displacement can be given as 2a cos theta. Okay, so VR1 minus VR2 is actually going to be minus E into 2a cos theta. Okay, so putting these values in the equation, then we will get that, minus PE cos theta that we saw before. Okay, and adding this work also. Okay, this work also, and that this is the final equation that we get. Okay, this is due to the external field that because of the torque that is being that is acting on the dipole, and this is the work being done when we are trying to get a unit positive charge, okay, against the field from R2 to R1. Okay, so now you can see this u prime theta actually varies from u theta that we got before, okay, by a quantity that is which is just a constant for a given dipole. Okay, so we consider the constant to be insignificant for potential energy, so we can drop the second term. Okay, and now you see that we took q theta 0 is equals to pi by 2. Okay, so in that case, the work done against the external field in bringing plus q and minus q are equal and opposite, and they cancel out. Okay, because of if we take as theta 0 as equals to pi by 2. Okay, over here if you again put pi by 2, so it's going to get 0, and we have also dropped this term. Okay, so this is the the effect or the kind of influence of the external field that we see on the when we are trying to calculate the potential energy, okay, of a dipole when there is an external electric field present. So now we saw that there are some phenomena that are associated with charges. Okay, so we had first started with electrostatic force. Okay, the charge first, then we saw electrostatic force, then we saw electric field. Okay, we then came to electric potential, electrostatic potential. We also learned about potential energy. Okay, so mostly these are these are properties of material that is that can conduct electricity, or which has some charge in it which can freely move, okay, from one point to another maybe. So conductors that we are considering are actually mobile charge carriers, and usually metals are good conductors, and these have and the charge carriers that are there in these metallic conductors are actually electrons. So how the electrons help in aiding in these metallic materials to be kind of be conducting in nature is that there are some valence electrons, okay, in metals which can part away from the atoms. Okay, they can move away from it, and they are free to move. Usually they are free to move within the metal. Okay, so they do not leave the metal. Okay, so they are there in the metal, but they can freely move within the metal. Okay, so the positive ions or the positive charges that we consider for a conductor is actually going to be the nuclei, which has both neutrons and protons, and the electrons that are there in the atom. Okay, they are giving you the negative kind of charges, and they are kind of held in their fixed positions. Okay, so these are conductors, and these are how the charge carriers are present in the conductors. Now there are a few important properties when we are considering conductors, and with respect to say electric field, electric potential, or the charge density or the charge configuration that is associated with the conductors. So first, as we know that a conductor will have free electrons. Okay, as long as the electric field is not zero, the free charge carriers would experience force and drift. Okay, so this is in a general sense. Okay, if electric field is there, the free charge carriers would, they try to move as per the field that is present. So in static situation, okay, in static situation, the charges are, so distributed or positioned that the electric field is going to be zero everywhere. Okay, so that is why we can say that inside a conductor, the electrostatic field is zero. Okay, so this is one of the first properties when we are considering conductors. Okay, and the next property is that as we had also seen before, okay, when we were trying to understand the charge, sorry, the electric field over a surface. Okay, suppose there is a charge configuration that is there over a surface. Okay, so if suppose we say that the electric field is not normal or not perpendicular to the surface, then we will have a non-zero component along the surface. Okay, so the free charges on the surface of the conductor would then experience force and move. But in static condition, we have seen that the electric field should have no tangential component. Okay, so that is why we can say that the electrostatic field at the surface of a charged conductor must be normal to the surface at every point. Okay, we had seen even before that this is there, that the electrostatic field that we see at any surface, okay, even when we are considering different kind of examples, that it is normal to the surface of the conductor. Okay, so electrostatic field is zero inside a conductor, and electrostatic field must be normal to the surface at every point. Okay, then if we are considering a neutral conductor, okay, so there will be equal amounts of positive and negative charges in every small volume or surface element. Okay, we actually consider the entire volume or entire surface to be made up of small element volumes, and for a neutral conductor, all these elements, okay, all these small elements, either volume or surface, will have equal amounts of positive and negative charges in them. When the conductor is charged, okay, the excess charge that is going to be produced, okay, it will reside only on the surface in static situations. Okay, so if we are considering a closed surface S, okay, and it is actually enclosing a volume V, there will be no charge, no net charge inside the conductor, and the excess charge that is there, it actually resides at the surface. Okay, this we saw as an example when we were considering the thin spherical shell. Okay, when we were trying to understand the electric field or electric potential at a point outside the shell and the inside the shell. Okay, so there is no electric field inside the shell since there is no charge being enclosed so inside the shell, but at any point outside the shell we have an electric field. We can also find out an electric potential. Okay, because the charge is actually residing on the surface of that shell. Okay, so this is how we know that there is no net charge at any point inside the conductor, and excess charge will reside at the surface. Okay, now since E inside the conductor is zero, okay, and it has no tangential component on the surface, so we can say we can conclude that no work is done in moving a small test charge within the conductor and on its surface. Okay, electric field is zero inside the conductor, so there is no work being done in moving any charge inside the conductor, and there is no tangential component on the surface, so there is no work needed to be done even on the surface of the charged conductor. Okay, so that is why we can say that there is no potential difference between any two points, okay, inside or on the surface of the conductor. Okay, so this is your conductor, so there is no work being done inside the inside the conductor as well as on the surface of the conductor. Since there is no electric field and there is no tangential component on the surface, there is no work being done inside as well as no work being done on the surface. Okay, so this means that if the conductor is charged, electric field normal to the surface is going to exist. Okay, so the mean potential will be different for the surface and a point outside the surface. Okay, so the potential over here on the surface is going to be different from any point that is, or suppose we are considering, okay, so we are considering an equipotential, surface over here. Okay, and this is a point. So the potential and the electric field is normal to the surface, and the potential at the surface is going to be different from this point that is outside the surface on an equipotential surface, suppose. Okay, so this is another aspect of the conductor. Now if we want to find what would be the electric field at a surface of a charged conductor. Okay, so we saw that the electric field or the electric potential will be different at the surface and at a point outside the surface. Inside the conductor we saw that the electric field would be 0. Okay, so for finding out the electric field because of at the surface of a charged conductor, we are going to consider a Gaussian surface which is going to be in the form of a short cylinder. Okay, so this short cylinder is partly inside the surface and outside the surface. Okay, it is enclosing a cross section. Okay, so this cross section is del S. Okay, and the height is we are ignoring it. So just inside the surface the electrostatic field is 0. We already saw that. Okay, and just outside the field is going to be normal to the surface. Okay, this is the field and this is the surface, so you can see the electric field is normal to the surface and the magnitude is E. Okay, so what is going to be the flux that is coming through the cylinder or the pillbox that we are considering? It is only with respect to the outside cross section. Okay, so we are not considering this surface anymore. We are going to consider only the surface that is outside the conductor, the surface of the conductor. So as you know, flux is actually E into del S or E into area. Okay, so what we find that the total flux through the Gaussian surface that we are considering is E into del S. Okay, plus minus. If your surface charge density is more than 0, it is going to be positive. If your surface charge density is less than 0 or in a negative, the flux is going to be negative. We are considering it for a small area del S. Okay, when we are considering it over a small area del S, okay, electric field can be considered constant. Okay, and E and del S can be parallel or anti-parallel, okay, with respect to the direction of the electric field. So to just get the magnitude of the field that is there, okay, electric field on the surface of the charged conductor, we are going to take the mod of the surface charge density sigma. Okay, so you can see the total flux E del S is equal to the the flux that we use as the Gauss's law. Okay, so we are going to get it as sigma mod of sigma del S upon E0. Okay, so we cancel out del S and del S. What we are left with, the electric field is equal to the mod of sigma upon epsilon 0. Okay, if sigma is more than 0, the electric field is normal to the surface and it is going radially outwards as it is there in the figure. If your surface charge density or sigma is less than 0, it is negative. Your electric field is normal, but it is going to be to the surface inwards. So the direction of the electric field will be opposite of what is being shown here. So this is how we find the electric field at a surface of a charged conductor. Now we come to something called electrostatic shielding. Okay, so for that we are going to consider a conductor with a cavity, and this cavity has no charge inside. Okay, no charges inside the cavity. So when we try to find the electric field inside the cavity, the result is that it is actually zero, no matter what is the size and shape of the cavity. Okay, see, you can see over here, suppose this is your a kind of conductor, and this is, say, your cavity. Okay, so we have found that the electric field in these kind of cavities are actually zero, no matter the size and shape of the cavity, and whatever charge is there on the conductor and the external field in which it might be placed. Okay, whether it is the conductor is charged, or there is a charge induced on a neutral conductor by an external field, any kind of all charges that are going to be there, okay, due to the conductor being charged, or any other charge being induced on a neutral conductor, it's only going to be on the outer surface of the conductor with the cavity. Okay, but inside the cavity it is going to be zero. So whatever be the charge and field configuration outside, any cavity in the conductor remains shielded from the outside electric influence. Okay, so the cavity that present in a conductor is going to be, it is not going to be affected by that electric field, either by the charges that is there on the conductor or by any external electric field. Okay, the field inside the cavity is always zero. This is known as electrostatic shielding. Okay, so the cavity is going to remain shielded from outside electric influence. Okay, so the effect can be made by using a protecting sensitive instrument from outside in electric influence. Okay, so this cavity can shield anything with respect to the from the influence of the outside electric field. So these are some kind of configurations where you can see the shape or charge the is not affecting. Okay, and inside, suppose this is your entire conductor and this is a cavity inside, you can see that the electric field is zero and the surface charge density is also zero. Okay, and you can see that even the electric potential inside this cavity, suppose, is also is equals to potential at when the electric field is kind of zero. So now we come to the other part, that is dielectrics. Okay, dielectrics are actually substances. These are non-conducting. Okay, so we spoke about the conductors. Now we are going to talk about a substance that is non-conducting in nature. Okay, so it is in contrast with the conductors. Okay, so they have no or very negligible amount of charge carriers in it. Okay, you can see in the diagram over here. Okay, there are charges, okay, but the number of charge carriers is negligible, or it will have no charge. Okay, so the free charge carriers move, and the charge distribution in the conductor actually adjusts itself in a way that the electric field due to the induced charge opposes the external field within the conductor. Okay, so this is your say, suppose this is your external field and this is your field induced. Okay, so this is they oppose each other within the conductor. Okay, this will keep happening until in a static situation, this will keep happening until the fields cancel each other and the net electrostatic force in the conductor is actually zero. Okay, so if we keep the conductor, okay, in the in an external field, okay, so the charge that is being induced due to the effect of the external field, okay, it's going to keep inducing until and unless the external field and the induced electric field is, kind of they are cancelling each other out, and the net electrostatic force is going to be zero. What happens in a dielectric is that the free movement of charges is not possible. Okay, that is possible in the conductors, that is not possible in the dielectrics. Okay, and the external field induces a dipole moment by stretching or reorienting the molecules of the dielectric. Okay, so the collective effect of all the molecular dipole moments is net charges on the surface of the dielectric, okay, which then produces a field that opposes the electric field. Okay, so as we saw in a conductor, the electric field due to induced charge opposes the external field. Okay, over here there is no induced charge because there is, the amount of any charge carriers are not there, but you have molecular dipoles that are being forming. Okay, and the collective effect of all the molecular dipole moments is going to, create the net charge on the surface of the dielectric, which will then produce an electric field, okay, that is going to oppose the external field. E0 is your external field. E induced over here is due to the, the net charge on the surface that is being, produced by the molecular dipoles. Okay, but in conductor, as you can see that they cancel each other out, okay, in the, while opposing each other. In dielectric, okay, in dielectric, the opposing field is so induced that it does not exactly cancel, okay, so it does not exactly cancel the external field. It will reduce it, but it will not be zero, okay, it will not cancel each other out. So that is why, this is the nature of a dielectric. Okay, so the induced electric field, okay, because of the, kind of reorientation and the stretching of the molecular dipoles, okay, is going to reduce the external field. It is not going to directly cancel the external field. Okay, so to understand the nature or the effect of this, kind of induced electrical field and how it is affecting the external field, we have to look at the charge distribution of dielectric at molecular level. Okay, so molecules of a substance can be polar or non-polar. Okay, so polar and non-polar. What are non-polar molecules? Okay, where the centers of the positive and negative charges are coinciding. Okay, the molecule that has no permanent or intrinsic dipole moment. Okay, so it does not inherently have any dipole moment. So examples would be your oxygen molecules and your hydrogen molecules. Okay, because they are symmetry. Okay, they coincide. There is a symmetry there and they don't have dipole moment. But for polar molecules, okay, so the centers of positive and negative charges are separated even when there is no external field. Okay, so they inherently have a permanent dipole moment. Okay, so that is why they are non-polar. Sorry, that is why they are a polar molecule. An example would be a hydrochloride, okay, HCl, or you have the water molecule. Okay, so in an external electric field, the positive and negative charges of a non-polar molecule are displaced in opposite direction. Okay, you can see this is when, there is no electric field. Okay, and when there is electric field, okay, so they are being displaced, okay, in opposite directions. The displacement stops when the external force on the constituent charges of the molecule is balanced by the restoring force due to the internal fields in the molecule. Okay, so there is some, say an internal field. Okay, so the non-polar molecule develops an induced dipole moment. Okay, and the dielectric is then said to be polarized by the external field. Okay, so this material can be dielectric. Okay, and the dipole moment that is being induced is due to an external field. Okay, where the E is not equal to 0, that means an external field is being applied. Okay, so the induced dipole moments of different molecules can add up to give you the net dipole moment of the dielectric in the presence of an external field. Okay, so this is how, a non-polar molecule can induce a net dipole moment in the presence of an external field. Okay, but when we are considering polar molecules, okay, so they can also develop a net dipole moment in an external field, but the mechanism is different. In the absence of any external field, the different permanent dipoles are oriented randomly due to thermal agitation. So the total dipole moment is zero. Okay, so when an external field is applied, the individual dipole moments will try to align with the field. So when you sum over all the molecules that are present, the net dipole moment will be in the direction of the external field. Okay, so then you can say that the dielectric is polarized. The extent of the polarization depends on the relative strength of two mutually opposite factors. The dipole potential energy in the external field, that is, trying to align the dipoles with the field, and the thermal energy that is trying to disrupt the alignment. Okay, so there is one force and there is one opposing force. So we can say that the induced, a dipole moment effect as for non-polar molecules, okay, it could be there, okay, where you are inducing the dipole moment as we had seen in the non-polar molecules, but the alignment effect is more important for the polar molecules. So in either case, whether polar or non-polar, a dielectric can develop a net dipole moment when it is placed in an external field. Okay, and the dipole moment per unit volume is then called the polarization, and it is denoted by the letter P. Okay, so for linear isotropic dielectrics, okay, so you can say P is equals to epsilon 0 chi E, E, the electric field. Okay, so chi E is the constant characteristic of the dielectric, and it is known as the electric susceptibility of the electric medium. Okay, so this is how we can understand the polarization that is being induced in a dielectric material. Okay, and the the strength, the extent of the polarization will depend on the strength of the external field, the dipole potential energy due to the external field, and also the thermal energy that is kind of opposing this. This is for your polar molecules. Okay, as you can see, suppose we are considering this dielectric slab. Okay, it is in an uniform external field. Okay, and it is the parallel to two of its faces. Okay, two of its faces. The field causes a uniform polarization P of the dielectric, as we already saw, and every volume element of this dielectric will have a dipole moment, okay, P into del V, that is a polarization into del V in the direction of the field. Okay, so then anywhere inside the dielectric, the del V will have no net charge. Okay, because you can see that the plus and minus of the dipoles is actually next to each other. Okay, so that is why, but the surface of the dipoles are going to have some charge. Okay, you can see that most negatively charged part of the dipoles are on the left hand side, and on the right hand side you can see the positives. Okay, so the positive ends of the dipoles remain unneutralized at the right surface. Okay, at the right surface, and you can see that the negative ends are on the left surface. The unbalanced charge are the induced charges due to the external field. Okay, thus the polarized dielectric is equivalent to two charge surfaces with induced surface charge densities. Okay, you have sigma p and sigma p. Okay, so this sigma p is due to the charge, the positive charges on the right side, and negative sigma p is due to the negative charges on the left side. Okay, so these are the two surface charge densities that we get. So clearly a field is being produced by these surface charges which opposes the external field. Okay, so the total field in the dielectric is thereby reduced from the case when no dielectric is present. Okay, so we should note that the surface charge density plus or minus sigma p arises from bound, not free charges in the dielectric. Okay, As we saw in conductors, the surface charge density happens because of the movement of the charges due to the placing of conductor in an external field. For dielectrics, it is due to the bounding of these charges to the surfaces. Okay, so it's not the movement of these are just the alignment of the dipoles in the dielectrics. Okay, so this is the difference between dielectrics and the conductors. Okay, so we are going to stop here today. So now after this we are going to go into a little more about dielectrics and also capacitance, so that we will be covering in the next class. So thank you for attending this class. Hope it helps you all.